In this lecture, we want to prove an important theorem that the order of the kernel of an isogeny is equal to the degree of the isogeny. So we already know if you are given any isogeny like this, like phi, you can separate it out. So you can have the first part which is separable and the second part which is applying Frobenius n times. So this we have seen in the previous lecture. And now we want to show that the order of kernel of this isogeny is equal to the degree of the separable part. So our isogeny is given like this: P over Q S by T Y. So this is our isogeny in standard form. Now since our isogeny is a group homomorphism, rather than worrying about which points get mapped to 0, we just take one point in the image and then we count the pre-images of that point. So rather than taking 0, 0, we take a point AB. A and B we both set as not equal to 0. The reason why we are not taking 0, 0 is because then we have to worry about projective embedding into space. Then you know that point 0, 0, 0 in P2 does not lie in the space. So we want to avoid those problems, and therefore we will choose A and B as not equal to 0. And we know by group homomorphism we just need to count the number of pre-images of this point, and that will give us the order of the kernel, just all the cosets essentially. So if you count the pre-images, you get all the cosets, and you know that those things will lie in the kernel. So visually we have it like this. So say you have an elliptic curve, one is like this, and then you have another curve which is like this. So we have our isogeny going from here to here, and say you have this point AB right here. So we find the inverse image of this point here. So our isogeny is taking this elliptic curve to this elliptic curve, and we find all the points which get mapped to AB. So all these points, so say one of these points you denote by x0, y0. So all these points which are in the pre-image of AB, you count them. So you denote all these points here as SAB, that is all x0, y0 lying on this elliptic curve. You apply phi to it, they give you this point AB. So inverse image of kernel would also consist of the same number of points. So we are just worried about the order of the kernel, not exactly what points are getting mapped to the kernel, but the order of the kernel. And the group homomorphism gives us a good idea to do that by taking any point AB which you set as not equal to 0 and start counting its pre-images. So this we know now just because of group homomorphism. So this follows from the fact because phi, this isogeny, is a group homomorphism. So you just take pre-image of any point in the image and count the number of pre-images. So we will do three things, and that will prove our result. So the first is, we say number of these points pre-images of AB, set SAB, is equal to number of distinct values of x0. So number of distinct values of x0. Now this is easy to show. Ideally we should be counting both x0 and y0, but we will show that the value of y0 just depends upon x0. So obviously you plug in x0, y0 here. So if you plug in x0, y0 here, this is what we get. And this we are saying is B, because this is, you plug in x0, y0, like any element in this set AB, you get mapped to this. Yeah, so you get mapped to B. So x0, y0 will get mapped to B. So this is B. Now solve for y0, you can say B tx0 over sx0, and this makes sense because this denominator is non-zero. So you can solve uniquely for y given the value of x0. So value of y0 depends only upon value of x0. So we can only worry about these points x0. The second thing is, we will say that the number of points in this SAB is equal to distinct roots of a polynomial gx, and where this degree of isogeny is equal to degree of g, and g you set as p minus aq. So that is precisely, you are setting p by q. So we are setting this px by qx as a, and then you multiply throughout, you get p minus aq as 0. So p minus aq, so you multiply by q. So this is 0. So rather than setting it equal to 0, you set it equals to, say, some polynomial g, so that when you take the roots, it's precisely when you take the roots that this equation is satisfied. So you have this equation g of x is, so this is nothing but g of x is equal to p of x minus a q of x. So you can solve for a when g of x is 0. So this is our g, and we will show that the degree of isogeny is equal to degree of g by making appropriate choice of a. And finally we will show that all roots of g are distinct. So we have already shown the number of SAB is equal to distinct roots of g. So then if all roots of g are distinct, then you have this equality here is equal to degree of g, because roots of g are distinct. We have, if we show this, if this is true, then this will follow here, and this thing here, kernel of phi is equal to number of points SAB, that is inverse image of SAB. This is coming from right here. So this will give us the required equality. So that is kernel of phi is equal to degree of phi, and this is what we wanted to show. So now let us prove 2. So for 2, you know that phi of x0 y0 is equal to ab. So that is, you're putting in x as x0 and y as y0. So obviously again we have this equation right here. So you can solve this. So when you plug in x0 in here, you get p of x0 over q of x0 is equal to a. And basically you again plug this in x0 here. So this implies what? This implies p of x0 minus a q of x0 is 0, but this you say is g of x0. So this first solution is for a if and only if our this g of x0 is 0. So that is, this thing is 0. So we choose a so that it is not equal to the ratio of the leading terms of px and qx. Now notice that what is degree of phi? So degree of phi is maximum of the degree of p and q. So we want to preserve this maximum degree, because we want degree of phi is equal to degree of g. So this can only happen if we preserve the maximum of degree of p and q. And to preserve the maximum degree of p and q, you have to make sure that the highest term does not get cancelled. So say p and q have the same degree, and if p and q have the same degree, you can choose a so that this highest terms can get cancelled. So what you do is you make a choice of a so that the highest degrees do not get cancelled, and that's the story. So you make sure that a does not have the ratio of leading terms of px and qx, and that will ensure that our maximum of p and q, the maximum degree of p and q is retained. So degree of isogeny is equal to degree of g. So this is also done. So the only thing we have to show is number 3, that all roots of g are distinct. So we have to force this. Now there are infinitely many choices of a and b. So first of all, we have made a choice here so as to show that a is not equal to the ratio of leading terms of px and qx, and we will make another choice of a, b so that the roots of g are distinct. So when are the roots of g not distinct? And then we will rule out the possibility of roots of g being not distinct. So if there is a multiple root, say x0 is a multiple root, then you will see that g of x0 is 0, and this is also equal to g prime of x0. So that is a condition for multiple roots, which we have seen in Galois theory also. So this is our definition of g of x from right here. Now take its derivative, you have p prime minus aq prime. So this is this. Now from these two equations, this and this, you can eliminate a. So from here you know that a is equal to p over q, and from here you know that a is equal to p prime over q prime. Now you can clear the denominators here and you will get this. And now we will say that there are only finitely many such x0 which satisfy such an equation. So if there are only finitely many such x0, then we can choose A appropriately to avoid these x0s. So notice that this isogeny is separable. So since this isogeny is separable, you know the condition for separability. The derivative of this has to be non-zero. So P by Q prime is non-zero. So P by Q prime, you know from elementary calculus, you get Q square here. You have Q P prime minus Q prime P. This is non-zero. That is just expanding this. And that means the numerator is non-zero. So notice that this is the same as this, bringing the terms to left hand side. So these two are precisely the same. So this is non-zero. So in general this is non-zero. So there are only finitely many x0. So this is a polynomial which is non-zero. So this is a non-zero polynomial. So this is a non-zero polynomial. So it has finitely many roots. So roots of this polynomial we can say are x0. So since therefore there are only finitely many such x0 that satisfy this equation, because this phi is separable. So now you know that you have infinitely many choices for A, B on this curve. So you can avoid these finitely many A, B which can give you a problem. So you avoid choosing those A, B. So therefore you choose A, B so that the above equation is not satisfied, so that you do not get roots for any of the pre-images, because this is a non-zero polynomial. It has only finitely many places where it will be zero. So you just pick those points where you do not have these roots, and you can pick that point because there are infinitely many such. So you can thus ensure that G has distinct roots by avoiding any such points. So we have proven 1, 2 and 3, which immediately implies that order of kernel of phi is equal to the degree of the isogeny. And notice that the definition of phi being separable has been chosen precisely so as to make this happen, that kernel of phi is equal to the degree of isogeny. So this isogeny is very interesting in the sense that you know the order of the kernel is precisely equal to the degree of the isogeny. Also, as an isogeny, you can split it into a separable part and a Frobenius part.